Also, now you have seen the most part for shear design. Today we're going to go through an example of show you how it's done. But you also notice that there's a difference, right, between the shear design code in ACI 2019, ACI 19 and ACI 14. And Ben, to your question, yes. So there's a discrepancy between the two design, right? And the main difference is that there's a factor in terms of size effect that has been introduced to the 31819 code. And that is based on, you can say, as a fracture mechanics approach, okay? Fracture mechanics approach. We will talk about those differences in terms of factors on Monday. So that will be a add-on to the shear design. But right afterwards, we'll be able to go through the one-way slab analysis, okay, after Monday, hopefully. All right, okay, so today I'm going to do some basic design for shear to give you an example what it looks like for shear design, okay? So let me share my screen. Okay, you can see it, hopefully. All right, so last time, so lecture 14, we talked about the shear design mechanism in terms of spacing, stereo spacing, and more importantly, we talk about the critical sections, right? So recall in lecture 14, we covered spacing design for stirrups, okay, and also covered the critical sections. Okay, so that's what we talked about before. Okay, so there are different scenarios. I don't want to waste too much time going over them again. Hence, just yesterday, so I hope it's fresh. But now, today, we're going to lecture 15. We're going to give an example on shear design. Okay, on shear design. Just to make you aware, okay, this approach right now is still ACI 31814. Okay. Now you may wonder why we haven't used 19 yet. It's just because the code 19 code right now released that is using a factor, but in your textbook that hasn't been updated. So we decided to teach you both. So we teach you 14 this semester, and with 19 on Monday to cover it. But from spring next semester, the new students, they will not probably be taught on 14 because at the time they graduate, they're probably only using 19 for design. Now, for all of you guys, folks who probably graduate, find a job soon, you probably apply 14, and some cases apply for 19 factors, which we'll talk about it on Monday, okay? But I would say there are still majority cases that 14 and 19 will give you the same design, okay? Same design, some cases, okay? All right, but let's take a look at the problem at hand first, okay? So example, okay? I have a section, right? I have a section, and this is old friend, rectangular section, nothing fancy. And I have a width of 12 inches, okay? 12 inches. And now I have four number 8 bars, at the bottom layer is tensile reinforcement, and the depth of that is 21.5 inches, so D equal to 21.5 inches. So that left us with a concrete cover of 2.5 inches. Okay, so this is the dimension. And just to remind us that height of the beam is D plus 2.5, that gives us a 24 inches. Okay, so this is the whole thing, right? So the questions are for beam given, for the section is given. Okay, so the section is given that we want to see if, check, okay, if the section is adequate. Check the section if it is adequate to resist shear VU, okay? And we'll give you a series of VU numbers, okay? And if not, okay, we need to design shear reinforcement, or we call it web reinforcement. They're the same thing, okay? Or design web reinforcement. Okay, and the materials property is given, F prime C for KSI. Okay, And FYT, which is yield strength of the stirrups, that is 60 KSI. That is 60 KSI. Okay. And to remind you, normal weight concrete. Okay. So this is a little bit new. Normal weight concrete means lambda equal to 1. All right. And simply supported beam. Simply supported beam. Okay. Simply supported beam. Okay. So let's take a look at it, right? So why is simply supported? Why is simply supported? Is that we are going to take a look at the critical cross sections at the end. So the shear diagram, there's some trouble going to sign. Okay, so the shear diagram looks like this. Right in the middle, 0, maximum end. Okay, so when we talk about the critical sections, it's going to be D, which means distance away from support. Okay, so these are the critical sections. Now we don't need it for this problem because I'm going to give you the numbers, but for the exam, you might have to use the shear diagram to determine the critical section first. Okay, but coming back to this problem, it's very simple. So VU, okay, is given. Now we have a multiple choices, right? So first part, VU is 12 kips. Okay, and second part, VU is 24 kips. Third part, VU is 54 kips. And last one, well, no, these 77 kips. And I forgot there's another one, which is 128 kips. Right? So essentially, we're trying to check if our section is adequate, which means the concrete contribution is adequate to resist this applied VU or not. And if it is not, what kind of reinforcement we need to provide to achieve that, right? So solution of this problem solve, right? So start from A, okay? So VU from A given is 12 kips, 12 kips, okay? 12 kips. And phi VN, which is the design shear, has to be bigger than equal than VU, right? Has to be bigger than equal than VU, right? So let's check first, what is the concrete contribution, right? VC equal to 2 lambda square root F prime C BWD, okay? And that means 2. And lambda right now is normal weight concrete, okay? Normal weight concrete. So lambda equal to 1, all right? And then I have a square root of 4,000 unit PSI, okay? 4,000 unit PSI. And the width is 12 inches, and the depth is 21.5 inches. Okay, so this is the shear resistance from the concrete. So bring the older number in. I got 32.6 kips. 32.6 kips. And this number is pretty big, Okay, and now I apply a phi VC. Now strength reduction factor for shear always 0.75. Then multiply 32.6 kips, and that gives you a 24.5 kip. 24.5 kips. Okay, now you realize that this number is bigger than VU equal to 12 kips. Okay, now we should be happy, isn't it? Okay, so it is, bigger than VU, but to judge whether we need the stirrups or not, we cannot just do this. We cannot just do this, right? Instead, we have to show that phi VC divided by 2, all right, phi VC divided by 2, that is 24.5 divided by 2, gives us a 12.25 kips. Now this number is still bigger than VU, that is 12 kips. Okay, that is 12 kips. Okay, so this is the criterion we have to use to judge whether we need the stirrups or not. Okay, so in this case, we say, all right, so if phi VC divided by 2 is smaller than VU, we need a stirrup. But if it's bigger than VU, okay, only minimum web reinforcement is needed. Only minimum web reinforcement is needed. That means AV mean is required. Okay, AV mean is required. So this is first problem, right? First problem, not bad. Okay, so let's take a look at the second, right? We increase, in the second part, we increase the shear from 12 kips to 24, doubled it. Okay, so immediately you know from previous calculation, phi VC is equal to 24.5 kips. Okay, that itself is bigger than VU. That itself is bigger than VU, right? Which is 24 kips in this case. Okay, but half of phi VC still smaller than VU. Half of phi VC still smaller than VU. So we have to use spacing. We have to use stirrups. Okay, so what type of spacing we need for stirrups? So S max for spacing that equal to a smallest or least, let me use least of following, right? Least of 24 inches, so D divided by 2 first, D divided by 2, and that is 21.5 inch divided by 2, and that is 10.75 inch, okay? And 24 inch, right? And the minimum AVFYT divided by 0.75 square root of prime C and BW. Okay, so now what is AV, right? What is AV? So looking back, I have two legs in stirrups. I did not specify which type of stirrups I need. So I'm going to go ahead and say, now let's assume number 3 stirrups to be used. Okay, assume number 3 stirrups to be used. All right, for number 3, each leg is 0.11 inch squared. Okay, so AV equal to 2 legs multiplied by 0.11 inch squared, so 0.22 inch squared. Okay, all right, so now I can plug in, so this is 0.22 inch squared multiplied by 60 KSI, but let me convert it back to PSI, okay? 60,000 PSI, and divided by 0.75 multiplied by square root of 4,000, okay? Again, PSI multiplied by 12 inches, okay? And I get this number to be 23.2 inch, 23.2 inch. And don't forget, there's another minimum requirement, that is AV FYT divided by 50 BW, and that equal to 0.22 inch squared, 60 KSI, or 60,000 PSI, divided by 50, multiplied by the width of it, 12 inch. So I have 22 inches, right? So now the spacing requirement is the least of these 4 numbers. So now 10.75, 24, 23.2, 22. So here you go, right? The 10.75 is the answer, right? So governs. Okay, 10.75 inches governed. Okay, therefore, so S max, sorry, there we go. S max, maximum spacing allowed equal to 10.75 inch. That's the maximum spacing allowed. And put in the bracket here, this is for number 3 stirrups. Okay, this is for number 3 stirrups. Okay, now this is the maximum spacing. When you do design, you want a spacing that is smaller than the maximum spacing, isn't it? So I will just be safe. I will say, let's pick 10 inches. Let's pick 10 inches, okay, to be safe. So with this, I'll say use number 3 stirrups, okay, at a spacing of 10 inch. At a spacing of 10 inch. Okay, so that is the number 2B. Okay, so sorry for being late reading the message. 0.75 phi in these cases, yes. So phi, pay attention, for shears always 0.75. Strength reduction factor for flexure changes, but for shear is constant. Okay, all right. So next problem for C, VU equal to a bigger number 54 kips. 54 kips. Okay. Now in A and B, you can see that A and B, I only need a minimum reinforcement. Okay, minimum reinforcement. In the case A, really just provide a minimum reinforcement. Okay, you throw anything that will satisfy. Okay. Well, matter of fact, it have to compare to these two values, but they are easily satisfied. But for VU with 24 kips, that although the concrete part alone is larger than the required shear, however, half of it is not. So you have to consider four different spacings. Okay. And for VU to 54 kip, things a little bit different. So I want you to see that. So phi VC, right? Phi VC has shown from previous calculation equal to 24.5 kips. And this number is much smaller than the 54 kips. Okay, so in this case, we definitely need the stirrups. And these stirrups will be obtained through calculation. Okay, so with that, I go back to the design board. So phi Vn equal to phi Vc plus Vs. Okay, and this has to be bigger and equal than Vu. So Vs required, that is needed, stirrups need to be equal to Vu divided by phi, you know it's 0.75 minus Vc, and that is 54 kips divided by 0.75 minus 20, oh, wait a minute, so minus 32.6 kip. Okay, where is this 32 coming from? From Vc, phi Vc 24.5 kips, so Vc equal to 24.5 kips divided by 0.75 and give you 32.6 kip. Okay. All right. Okay. So that is the required shear from the stirrups. So before you do anything, okay, check, right? Check what? Vs required, okay, equal to a 39.3. Sorry, equal to a 39.3 kips. Okay, this is 39.3 kips after subtraction. Okay, that's the required shear from the stirrups. Has to be smaller than 8 times the square root f prime c BWD. Remember, that's the section check. And you plug this number in, this is 130.6 kips. So satisfied. Okay, and after that, let's check again. VS required, whether it's smaller than 4 times square root of f prime c BWD. Turns out this number is half of that, so 65.3 kips. Okay, so why are these checks? Okay, so if you forgot, let me just write out here. So this check is called a section size check, right? To check if the section is large enough, right? If it doesn't satisfy, you have to go back and change your geometry. And this is to check whether you need a double spacing. Oh, sorry, shouldn't say double, half, right? Whether you need a half spacing. If it's smaller than that, you don't need a half. If it's bigger than that, you need a half. Okay, you need a half, which will show. Okay, which will show. But anyhow, we're fine, right? We don't have to change our section, nor do we need to change the spacing for the stirrups in halves, right? So proceed with this. I'll say the maximum spacing, sorry, let me just jump page. I don't want to run across this. So the maximum spacing has to be the least of recall from previous equations, right? All these nice fellows. So D divided by 2, and we already got this number 10.75 inch again. And 24, we know that AVFYT divided by 0.75. Okay, 0.75 square root f prime c BW. Okay, and this is 23.2 from previous calculations. And also AVFYT divided by 50 BW, and you got this number from previous one, and that is 22 inches. But don't forget, there's a calculated one. Right? So calculated one says that is AVFYT multiplied by D, which is the depth, divided by VS required. VS required. So this is 0.22 inch squared. Why I keep using all these numbers? Because don't forget, right? All these are saying number 3 stirrups. Number 3 stirrups. We are using number 3 stirrups. Okay, we're using number 3 stirrups. Okay, so this is that, and this is 60,000 psi. Okay, and I have a 21.5 inch of beam depth divided by required shear, that is 39.3 kips. So 39.3 multiplied by 1,000 pound LBF. Okay, LBF. LBF. Okay, so you carry out the calculation, show this number to be 7.26 inch. Okay, just to be consistent, let me use the simplified mark. All right, okay, so that's all. That's all we need to do for this, right? So these are all the spacing requirement. Now, again, the spacing is the least of all these numbers, all these 5 numbers, right? And I have a 10.75, 24, 23.2, 22, 7.26. Which one is the smallest? Of course, this fellow right here. Okay, this fellow right here. That's the lowest number. That is the lowest number. Okay, so now what I'm going to do, I say, okay, so all I have to make sure is that I'm going to use number 3 stirrups for sure, but I want to have a spacing that is smaller than maximum requirement is 7.26 inches. Okay, and I can go 7, but 7 is really an odd number. Okay, so I would say, you know what, just to ease the fabrication, I am going to use, okay, I'm going to use number 3 stirrups. Don't forget, all these calculations are based on number 3 stirrups at a spacing of 6 inches. Okay, which is smaller than 7.26 inches requirement. Okay, half foot. All right, so this is problem number 3C. Okay, so quick recall, right? So this section, question? Any question for me?
Why did you use 6 inches? Did you just pick it randomly because it's lower than 6.26?
Yes, I can pick 3, but that's too greedy, too many stirrups. So I just want to pick a number smaller than that. You know, I figure by half foot it's just easy to count.
Okay.
Yeah, no special reason. Like I said, you can pick 7 if you want, as long as it's smaller than this number.
Okay, thank you.
Good deal. Okay, all right, so quick recall, see that we bump up the shear forces, right? Apply shear went up to 54, right? So we did all these nice check, make sure section geometry is right, don't need to have the spacing, and perform the calculation, arrive at this number. And I pick a lovely number that I like, just because it's easy to fabricate in terms of tying the cages. But I made sure that the spacing I provided is smaller than the largest requirement, which is 7.26 inches. Okay, all right, so that's that. Now, next one, let's move on, right? Let's move on, increase VU to even higher number, to 77 kips. Whoa, okay, 77 kips. Okay, that's pretty big. I think I lost you guys real quick. Let me just put you here. Okay, all right. Can you guys still see my screen? Hello? Anybody? Okay.
Yes, I can see it.
Okay, sorry about that. I just worry about this internet thing sometimes drive me crazy. Okay, good. So let me zoom in a little bit so you can see better, maybe, hopefully. Okay, so I increased my shear to VU to 77 kips, which is high, right? Which is high. So first thing first, okay, always check. So check, right? I need to make sure since that this number VU is 77 kips, that is much bigger than VVC. So naturally, concrete is not going to cut it. Just the concrete is not going to cut it. 24.5 kips. I don't like this pencil. Sometimes drive me nuts. Okay, 24.5 kips. Okay, all right. So this is the section. Sorry, this is the concrete check, meaning that we need the stirrups. So need stirrups.
I have a question real quick.
Yes, sir.
So for B, well, okay, for C, you did use that last equation for S max, the AV FYT times D over VS required.
Yes.
So why didn't you do that for B?
Well, for B, the concrete VVC, right, is bigger than VU. So in this case, right, VS required would be negative, isn't it?
Oh, okay, okay. So you use that equation when it's bigger.
Right. So that is to say that, in the very first one, even half of the concrete contribution is bigger than applied. So we just need to provide any stirrups, right? Something that will work, minimum requirement. Okay. For this one, although half of the concrete is not suffice. It does not work. Does not suffice. But the full PVC is bigger, right? So the entire concrete can take care of the shear, but we were required to provide stirrups anyway, but you don't have to calculate it because you don't have a number for the required stirrups anyway.
Okay, yeah, that makes sense. Thank you.
Right. Sure. Yeah, and then next one, now we bump up the shear even more, and turns out that the VS required is positive, right? And it has a big number actually. This is positive. So we do have to provide a calculation for it. So we add one more term to the spacing requirement, which is the last one, that need to be calculated. Okay, all right.
Yeah.
So we're just playing this game, right? We just, ante up, right? Get more, right? Increase the shear, apply shear force, see what happens. Right? So the next one, we increase even more to 77 kips, right? See what happens is now definitely the concrete cannot, satisfy the requirement. We need stirrups, so need stirrups. Okay, and let's proceed to calculate the required shear from the stirrups is equal to VU, which is applied, divided by phi, 0.75 always in shear, minus VC. Okay, that is 77 kips divided by 0.75 minus VC, right? VC is 32.6 kips from our previous calculations. So VS required in this case is big. It is 70 kips, much bigger than previous one. Okay, so what we do, we check, right? Don't forget, right? First thing is to check size, right? So size check to see if the section satisfied or not, right? So that is VS required will be compared, VS required will be compared to a 70, sorry, let me see. Sorry, 70, 8 times square root F prime C BWD. Now I did not write lambda here, okay? Lambda equal to 1, we already know it, okay? And from previous calculation, this number is 130.6 kips. So size is okay. Size is okay, right? But next thing is half the spacing, right? Do I need to reduce my spacing by half? Okay, so you run through that check, VS required equal to 70 kips. I told you sometimes acting weird. 70 kips, okay? And that is bigger. That is bigger than F prime C BWD, which is 65.3 kips. Okay, so this color, this means not gonna work. That means reduce spacing by halves, right? By 50%. Okay, so what does it mean, right? What does it mean? It means I'm gonna change my equation now. So S max that equal to a least of, right? Least of the lower number of following. Ooh, pretty long, following, right? So first thing first, half the spacing, right? 50%, so D divided by 4. D divided by 4, and that is 5.3 inches. Okay, now it was 24 in the previous case, now it's 12 inches. Okay, now the other things stays. AVFYT divided by a 0.75 square root F prime C BW, these stays, and that is 23.2 inches. And then AVFYT divided by 50 BW, Okay, and this is 22 inches stays. And now the calculation, right? The calculated one stays as well. This is AVFYT multiplied the spacing D divided by a VS required. Okay, VS required. And now this number 0.22 inch squared, I need to compute it, right? And 60,000 PSI multiplied by 21.5 inch divided by VS required, that is 70,000 pounds per square foot. Okay, turns out this number is 4.1 inches. 4.1 inches. Okay, so let me see. Okay, so looking back, it says has to be least of all these numbers, right? So I have 5.3, 12, 23.2, 22, 4.1. Which one governs? Of course, this is our winner, right? So the calculated one governs. The calculated spacing governs. Okay, so now my job is to provide a spacing. My job is to provide a spacing that is less than 4.1 inches. Okay, now not too hard to do. So let's use always forgot my color. So conclusion type. Okay, use number 3 stirrups at 4 inches. Okay, 4 inches. Okay, that should satisfy the requirement. All right. Okay, so you see, we're gradually changing the spacing from bigger to smaller as my shear force increases. My shear force increases. All right, so this is not over yet, right? We say, okay, you know what? We're not satisfied. We're not happy yet. Let me push to the limit. We say the applied shear now, let's increase to 128 kips. All right, that's pretty big. For a section like this, pretty big. Okay, so naturally, we know that VU at 128 kips is much bigger than VVC at 30 something, right? So needless to say, we need stirrups. We know that from previous experiences. Okay, we have to provide stirrups. Don't even worry about it. You just have to do it, right? And now, supposedly, I should just calculate required shear from stirrups. That is VU divided by phi minus VC. So this is 128 kips divided by a 0.75 minus a 32.6 kips. Okay, and I have a 138 kips. Sorry, yes, 138 kips. Okay, so huge number, huge number. Okay, so I need to make sure that this is okay with my size first. So check, right? First thing first, check size, right? Section size, right? So this number here, oh, color. Okay, VS required equal to a 138 kips. That is even bigger than the A times square root F prime CBWD. Okay, even bigger than that, right? What's that number? What's the number? Is 130.6 kips. 130.6 kips. Okay, even bigger than this number. Okay, all right, so fails. Okay, fails, right? What does it mean? It means job is over, right? It means I will stop calculating. I'll say, you know what, guys, cannot take this too much. Go back to increase your section. Okay, increase the section. All right, that means previously you have a section of 12, right? You have previously 12 to 24. Right now, the best approach, if I want to maintain my moment capacity, I don't want to increase my moment capacity too much. I'll just say maybe increase the width to, right? Since this is 38, this is 30, so little bit, just a little bit, so I can go 16 inches in width and keep the height. And that's one option. Or I shouldn't say increased. My tense is messed up today. Okay, anyway. So, or you say increase F prime C. Now was 4 KSI before, let's do 6 KSI. Okay, if you do 6 KSI, you will be okay. You'll be okay. All right. So folks, there you go. This is the entire shear design. Shear design given the VU, given the VU. Okay. All right. So it's quite a bit. We have varied different numbers. Okay. So you can see that as I increase my shear, beginning I don't even have to have a stirrups, just minimum will suffice. And then I have to use the spacing requirement, go on to find the least spacing. And then I have to calculate it and use the calculated spacing. Okay. Then I reduce the calculated spacing even more. At the end, my section is not even big enough. I have to change my section to accommodate the shear resistance. All right. Okay. So this is it. This is how we calculate for shear. All right. Any questions, folks?
Bob, I got a question on part D.
Yes, sir.
So when we did our checks, it said we failed the second check, so it said reduce our spacing by 50%.
Uh-huh.
Oh, okay, never mind. I see what you did.
Yeah. So
you took our requirements like D over 2 and made D over 4. And,
yes.
That makes sense.
Yeah, it was.
I was thinking that we had to take our final S max and divide it by 2.
I see, right? So let me just write down here so I won't be confused, right? Compared to the previous case, which was D divided by 2, right? So this is same thing. This is 24 inches. Got it, right? So only these two. Only these two. Okay. All right. Anything else, folks? This is very important. Okay. This is very, very important. Anything else?
Hey, Bob, I have a question about AV.
Yeah.
I realize it's the cross-sectional area of the stirrups.
Yeah. Yes.
On our quiz, we had to do that as well, and I went back and looked in a note before the quiz 6, and I think you in your notes it was labeled a little bit differently than how you just did it.
Did I make a mistake?
I think so.
Okay, let me go back and check and correct that. But let me clarify here.
It's in lecture 13.
13. Okay, let me go. So correct lecture 13. All right. Let me just make a mark here in case I forgot. All right. I provide a correction later. Okay.
Okay.
Yeah, but I mean, let me just clarify before we go, right? So everybody's here. So this is number 3 in the 3D setting, right? Can you see it? Right. So this is the hook, and there's just side view kind of, right? If you look at from the front view, it looks like this, right? So all we need to do is you cut one here. This is 0.11 inch squared, right? You cut one here. This is 0.11 inch squared. All right. So if you do a cross-sectional cut, you have 2 cuts basically, right? So the total AV equal to 0.11 inch squared multiplied by 2. That is 0.22 inch squared. This is correct. Okay.
Okay.
Yeah, this is correct. I may have made a mislabeling before. I'll go back, correct it, but this is correct.
All right. Thank you.
Sure, no problem. Anything else, guys? Are we good, folks? Anything else? All right. So this is a good point to stop. I'm going to stop here right now. We're welcome to stay if you have any question regarding homeworks or regarding to the lectures, anything else, okay? And let me answer one question from chat here. Is there a table for startup dimensions? Ben, if you go to table A5, I believe, in the textbook. Sorry, table A1, okay? Table A1, that should have all the bar size. Okay, so it's the same thing, right? Stereo dimension is always number 3, number 5. So number 3, in the bar table, you have a diameter 3/8, but area is 0.11 inch squared. But you have 2 legs, right? It bends, right? So multiplied by 2, that is 0.22. Okay, you always have to do this. Okay, all right, okay. So let me stop record.